Well, I really appreciate all you being here. It's good to be back for the second year in a row. Today, I'm going to be talking about what makes software projects so unpredictable and what we can do about it. So you may have noticed this is the deep learning track, and I'm coming at deep learning from a bit of an angle, and that is that if we can understand how the brain works, that will, A, help us humans solve problems better, but B, it might also shed light on how machines might solve these problems in the future. And being an engineer, this is kind of the area I'm focusing on. How do we become better software engineers? So I should remind you before I jump in to please rate, because I'd love to get your feedback, and there will be a couple minutes at the end for questions. And also, I'm going to be mentioning a bunch of projects, blog posts, etc. So don't worry. I have a GitHub link up here that has all the links in detail there, so feel free to follow along there. So just want to tell you a little bit about myself first. Aristotle once said that for the things that we have to learn before we do them, we need to learn by doing them. And so the question that I'm wrestling with is, what is intelligence? How does it work? And what is, in particular, the simplest possible way we can describe intelligence that is confirmed by what we see in the world around us, and also that we could confirm in science? So the way that I'm tackling this question is, in 2014, I co-founded a company called Order of Magnitude Labs. And so we're learning about intelligence by attempting to build intelligent machines. And through this process, I've started to kind of take a step back and thinking this through, and it's led me to start to see the world in a new light. And being a software engineer, I've kind of applied this thinking to software engineering and come up with kind of some different angles on it that I hope to share with you today. So we're going to discuss a big reason why software projects are unpredictable. We're going to talk about how we can better help computers understand what we mean, and how can we help them become more resilient, more self-sufficient in situations of stress that we didn't necessarily predict. And then lastly, to close the loop, how can we better understand what our software systems are doing? So we're going to start with a little story. This story is about an egg. It's very short because the egg can't really do anything. It's just sitting there. So along comes this spatula, and the spatula takes the egg and turns it into a scrambled egg. So that's kind of sad because there was really nothing the egg could do. So let's do a little thought experiment. What if that egg instead had a face? So it could look around and see the world around it. And then we add one more ingredient. It has legs. So it can move around and see the world from different perspectives. So now if we add a third ingredient, let's say the egg has a brain, that same spatula comes along, the egg is going to see it coming along, and then it's going to run away. So it's going to prevent itself from becoming that scrambled egg. And in my mind, this is really the simplest description I can come up with for life. So really the main ingredients for life are you have a set of senses and actuators. If you were at the keynote this morning, you might have seen that this is pretty similar to what was talked about there, with having actuators, sensors, and the bit in the middle is really computation, but what I'm describing it is as a generative model. And so the generative model essentially interprets what's coming in through the sensors, and it's generating perceptions about what it's seeing, and then it's also generating action as well. And in some sense, this is really all we need to survive. So we're trying to navigate this imaginary bubble up here that entails our predictable, happy states. This is really our survival. And we use our generative model to find where's the boundary and how do we stay within that boundary? Because we want to be here in the survival zone. We don't want to be out here. So the neat thing about this is we are creatures that have evolved over millions of years, and we have very developed sensors that are going to help us stay inside that bubble with very little cognitive effort. So, for example, if I see a tiger coming from 200 yards away, 200 meters away, I'm in Europe, then I don't have to stop, look, and go, what is that? What should I do about it? Because by the time that amount of time has elapsed, I'm already running in the other direction. So, what if you are a particular kind of human, though? What if you're a software engineer? And your job now is a little bit more complicated, because not only do you need to survive, but you need to map out a magic bubble of working software. And you need to stay out of this zone of not working software. Except the problem is, you don't have a highly developed set of sensors that have evolved over millions of years to immediately tell you in a blink of an eye, oh, this is working software and this is not working software. No, instead, over the years, as you've developed your skill of engineering, you have created a set of heuristics, a set of, if you will, high-level sensors in your brain that are going to tell you with some mental effort whether something's working or not. It's a good thing that our immediate survival usually doesn't depend on this, but in some situations it actually does. So here's the thing. As an engineer, you actually have one level of indirection added to challenge you a bit. The software that you write itself can be thought of as a generative model of sorts, in that it's taking input coming in from the world that maybe other software system is interacting with, and it's generating some output that needs to have some behavior that matches what you expect. But there's something different about this generative model than your brain. We all know that code and brains are not the same thing. I think a key difference in my mind is that the generative model is infinitely precise. So you misplace one character, the entire meaning of your code can change. There's no tolerance for sort of noise and uncertainty that we all can interpret in our brains coming from the real world. So I'm going to come back to this point in just a couple slides. So imagine you're the typical software engineer, and your boss comes in and says, oh, we need to add this new feature to our product. So you go, okay, I'm going to think about that. You spend a couple days working out a design. Your colleagues challenge you with questions, oh, is this going to work, is that going to work? And every question you can answer. And you realize this is going to be great. So you start implementing it, and pretty soon you're in the zone. You lose all track of time, and you're just imagining how great this feature is going to be once you release it to production. So finally that big moment comes, the moment of truth, and then this happens. Oh my God. What happened? I did not tell the robot to kill people. That is absolutely terrible. So what happened is you thought that you were in this happy little zone of, hey, everything is working and everything is fine. But in reality, you are way out here, right? And this is in part because you're working indirectly through this generative model called code without the use of senses to guide you. So let's go and look at this code. Raise your hand when you see something wrong with the code that was written there. All right, somebody. Okay, see a few hands. All right. So if you didn't notice, this is most likely C code based on the syntax. And this here is an assignment operator. And that's actually a really bad thing in an if statement. Some languages wouldn't allow this to compile. So unfortunately, you're always going to end up killing humans. So I want to point out a couple things about this code. First of all, I don't think any of you, within a couple hundred milliseconds of seeing this, except maybe that one guy over there, I was pretty impressed at how fast that hand went up. I don't think any of you would be able to say, oh my God, the code is not working. I need to run away because there's going to be murdering robots. This is awful, right? You had to step through, spend a few seconds thinking through what could possibly go wrong and what the nature of that is. The other piece that I want to point out is that, a single character here was missing. This is exactly what I mean by infinite precision, right? You're trying to create some behavior in this robot, but one thing goes wrong and you're falling off the cliff. So contrast that with human-level precision. If I'm going to give instructions to a human, I could tell them something in any number of ways, maybe even an infinite number of ways, right? Be nice to people, respect human life, don't hurt people, right? That person, if they followed my instructions, would probably end up not killing human beings, right? We live in this noisy, limited precision world, and our brains, our generative models don't have any problem with that. But if you're the computer, you have to be right on target, because if you're here, you're going to end up with these crazy murdering robots. Oh my God. So here's another way to look at it, okay? Usually the first thing you think about when you're designing a system is, what is the happy path, right? And if you think of that and nothing else, you're going to wind up generating something where the landscape looks something like this. Happy, happy, happy. Oh my God, utterly broken, right? This is really the cliffs of infinite precision that we really want to avoid. So all is not lost, though, because we can change the landscape a bit. What we'd rather have is a model where we think of sort of the top of a gentle slope with optimal states up here. And when the noisy chaos of the world comes in, you descend the slope in a gradual way where you're degrading. And not only that, but without human intervention, your system will be resilient, as in it can climb back up to the top with these optimal states when the stress goes away. So today I'm going to talk about how we can do this. We can't make the computer less precise, but we can cheat. So several ways we can do this are we can think of testing in terms of testing properties. We can do remedy first design. You probably have no idea what that is till I talk about it. And we can build intuitive insight. So these are just several ways to get you thinking about how can we change the landscape of the software that we produce. So let's talk about property tests. So imagine that you've never seen a rubber ball in your life, and somebody hands you a tub of rubber balls. And they just say, hey, fiddle around with them and see what you think. So you start picking them up. Some are big, some are small, different colors. And sooner or later, you drop one on the ground, and you notice something odd happens. It bounces. And you keep playing with the balls, and you drop another one, and that one bounces too. Pretty soon, you're throwing them on the ground going, wow, this is neat, they all bounce. A week goes by, and your friend has a ball, and you say, hey, can I see that? You pick it up, and it bounced. So what did you learn here? You learned a property of rubber balls that they bounce. You didn't need to see every single rubber ball in the universe to kind of have this idea that if you pick up a ball, it's going to bounce. What you didn't learn is, hey, this blue ball bounces, that red ball bounces. No, you were able to generalize to a higher degree. So what we can do is take this idea that's very natural in how we learn and how we see the world and apply it to how we do testing, which will have a ripple effect into how we even think about our systems as we design them. So I'm going to take a slight detour until we get back to this point. Hopefully it'll become clear in a few slides. So getting back to the notion of code being a generative model, well, your test is code that you wrote. And so in a sense, it's a generative model. But what it's trying to generate in this case is actually training examples. So if you're training a neural network as in a supervised fashion, right, you want to give it a bunch of inputs, X, and you want to change the weights so that it will produce some test outputs Y, essentially. So instead of, say, doing back propagation gradient descent on a neural network, when it comes to test suites, we're providing test results that we give to humans to train the humans to write better code, essentially. So when you start to think of testing in this way, you kind of start to realize, hey, if we just do unit tests and nothing else, there's kind of a data problem. Because the way most unit tests are written is, oh, well, I'm going to hand code a specific training example, if you will, and I'm really going to cross my fingers and hope that it represents this larger bubble of state or behavior that we're trying to test. So let me give you an example. This comes from a fantastic blog post. It's about property testing in F#, but you don't have to be doing F# to get a lot of value out of it. I don't know F# myself. So this test is essentially trying to test a function that adds 2 integers, nothing exciting, but it only provides one training example, right? 1 plus 2, I expect to get 3 back. So your test passes, and you deploy it to production, like, yay, it's all going to work. But it fails spectacularly. So what went wrong here? Let's go back and look at the test that we actually wrote, or the code that we actually wrote, and we find that, wow, this is overfitting, essentially, right? What you're saying is, well, when I get the training example, the test that I wrote, I'm going to give it the right answer. And any other answer, who cares? So really, all you would have to do in terms of your training examples to find the bug is kind of just take a 1 step to the left, and you would find that something was massively wrong. Right? This happens all the time if you're unit testing, right? You think that this one example you came up with is representative, and in fact, it's not. So let's change the way that we frame the problem, and let's go back to that idea of property testing, right? We want to be able to think of our systems in terms of the properties that it adheres to. We don't want to have to say, well, pick up this blue ball and it should bounce, pick up the red ball, it should bounce. We want to be able to say, no, any ball that has these characteristics on a hard surface is going to bounce. So what this does is it frees you up to generate very easily, using, let's say, random integers in this case, a massive set of training data. And you can surround your bug with your test. So what we're doing here, we take a random integer and we're saying, hey, let's test the property that you take the number x, any x, add 0 to it, and you're going to get that x back. Right? You can imagine maybe we're going to test the commutative property. No? Okay. All right, so maybe we're going to test the commutative property and swap the order of the operands. So when you start thinking in terms of the properties, it better matches the way that we experience the world, and it's more tolerant to sort of noise in the training examples, right? No matter what training example we throw at it, this property should hold true, and if it doesn't, then we have a problem. So let's review. We can think of our test suite as generative models. They're generating training examples for the system that we're testing. And if we're able to describe the properties of our system, then we will be able to do a lot less effort to test, and we'll get a lot better coverage that matches kind of this noisy, uncertain nature of the world, right? We can generate a much larger training examples. So let's talk about remedy-first design. And again, this is best described in terms of real-life experiences. So imagine you're standing in the middle of the street, and all of a sudden, a large, heavy object you can see out of the corner of your eye is coming toward your head. So it's time for a multiple-choice quiz. Would you A, turn, look at the object, try and determine what it is, what its trajectory, why it's flying at your head, where it came from, or B, would you jump out of the way? I don't know about you, but I would choose B. Because if I choose B, then A, I'm maintaining my original form, I'm surviving, and B, I have time now to go look, well, what was that thing? Where did it come from, and how do I avoid that? And so we need to start thinking this way when we're designing, building, and testing our software systems as well. We want to create software systems that are good at jumping out of the way when these big, heavy flying objects come at them, rather than being fixated on, well, why did this happen, and how do we fix it, right? If you can jump out of the way, you have plenty of time to go figure out why something happened. So let's go through an example. Let's say you're writing a client to a RESTful service, and you have this metadata request up here. And knowing nothing else about the client, or about the API, you get back this error code. Error code 234, what should we do about this? Let's say you fiddle around a little bit and you find that, if I retry, this doesn't happen again, I get the metadata back. So you just add a little hook to your client that says, hey, if I get error code 234, let's just do a retry. So everything's good, you push to production, but then something odd happens. You get error code 235 in production, and your client falls off a cliff of infinite precision because you wrote something in your client that deals with a specific cause, a specific error code, rather than kind of taking a step back and looking at what remedies you could apply. So you go to the service team person that came up with this API, and you go, hey, what gives? Where did this error come from? And they say, when we designed this API, we came up with a whole list of errors that we thought were going to happen. But then we got it into production, we found out, wait a minute, there's other errors that we need to start adding, right? There's more causes, and we want to have insight into these causes, and that's a perfectly reasonable thing to do. But you say, no way, there's no way I'm going to spend my time keeping up with adding all these error codes to my client. That's not a good use of my time. So then you both take a step back and start thinking about it a little bit more, and you realize that if you reframe this whole discussion to talk about how can we get our client to jump out of the way, because guess what? The client doesn't really care if there's a connection pool exhaustion on the server. The client just wants to do its thing and serve the user properly. So you start to group these errors in terms of what remedy can you apply in the moment so that the client can make progress. And specifically, I mean, maybe there's some set of errors that could retry. Maybe there's some that you would want to do a redirect for. Perhaps the user messed up and you want to display an error, right? It goes on. Maybe you want to re-authenticate. So the beauty of this is that there's far fewer possible remedies than there are causes. It gets you out of the game of having to predict what are all the possible things that could go wrong in my system, and gets you into the business of how do I react to failures when it's happening to then buy me time to figure out whatever causes happened. So really the takeaway from this is your guy added something to the protocol that says, here's an action. The client can just ignore this information. The client can just act based on what it's told to do. And then the server people can go work out what actually went wrong. So these are application level errors. But there's a whole host of other errors that are kind of below that level. What about things that happened in the cloud, for example, if you're deployed to AWS? AWS has had its ups and downs, and at any moment there could be sort of a service outage. So for example, in 2012, there was such an outage. It started with a failure to propagate DNS changes. That triggered this latent memory leak. The failovers didn't happen because the alerting wasn't set up right, and then customers got throttled and services went down. Now that is a very specific chain of events that happened that I don't think any one person could have predicted the timing of or the specifics of. So if we fast forward to 2014, there was a required security update to about 10% of EC2 nodes, and that meant a reboot. So if you're running a stateful application on EC2 and you haven't come up with a strategy to deal with reboots, you might be shaking in your boots at this point. Another one happened last year. There was a DynamoDB outage. Dozens of AWS services went out, and that took down quite a bit of the internet. So this is kind of just to give you an example, diverse examples of different types of failures that could happen. And what if I told you if there was one company that, despite making massive and public investments in AWS, was ready for all of these and was not affected by any of these incidents? So that company was Netflix. How many of you guys have heard of Simian Army? Okay, a few hands. Maybe a half, third of you guys, perhaps. So if you don't know what Simian Army is, It is an open source project by Netflix. And the goal of this project is to deliberately cause failure in a controlled manner in production. Okay, so let that sink in a moment. What? Deliberately cause failure in production. So the types of failure that it's going to cause would be, for example, taking out a random EC2 node, taking out an entire data center, taking out an entire region, right? These are kind of massive failures. There's another one that introduces latency. And the whole goal of this is to validate whether systems handle failure. So it was around 2011, 2012 that Netflix really started putting this idea of failure testing in production into practice. And I can say that that really caused a cultural shift in that failure became the norm. It became a topic of discussion at the very first design discussions of a new service. And I think the most powerful idea about the Simian Army is that it simulates the nature of the failure, right? Nodes go away all the time, data centers go away all the time. It doesn't try to simulate the causes. There was no knowledge of, oh, there's this DNS failure, and let's see what happens when we trigger a DNS failure. It was very much more broad and less precise, and kind of acknowledging the fact that we humans are terrible at predicting specific events, but we can get a general sense of the patterns of failure. So, just to review, when you're creating a system, you're designing and testing it, do it with remedies in mind. Think about how can you jump out of the way of that flying object, and how can you buy yourself time to go pick up the pieces later. This is actually a great thing because the number of remedies is far less than the number of causes. And I urge you to test your resilience during business hours. You may say, that takes too much time. I don't have time for that. Well, guess what? It's going to be tested for you no matter what. It's either going to be done because you did it on purpose or because something catastrophic happened at 3 in the morning and you got woken up. So let's turn our attention to intuitive feedback. We've kind of talked about, designing, building, testing our system, but how do we actually get information back out of the system that will help us point to whether there's a problem or not and where to go look next? So the place that we want to be is we want to be that guy, standing on the horizon, looking out at the landscape, and able to see in a blink of an eye, oh, there's a plume of smoke over there. Let's go look over there and figure out what's going on. So how do we do this today? One of the first things that a lot of us tend to do is we add logs because they're very easy to add to our code. You can produce a line of and all of a sudden you have huge log files, right? Okay, so this is not my favorite way of trying to get the lay of the land, because in my mind, looking through logs is kind of like you're watching a movie, one frame at a time, through a keyhole, basically. It's like, well, can you tell what's going on? Maybe if you cycle back and forth, and maybe if you have enough time. But when you're in the moment and you need to alleviate some kind of pain point, this isn't really going to be the most effective use of your time. And it also doesn't use our highly evolved, developed senses. It uses our heuristics that we have painstakingly built in our brains over the years that require a lot of mental effort to process. So let's turn our attention to charts. This is a much nicer thing to look at, and it adds a new dimension. There's time here. So you're seeing a lot more compressed, condensed information. You have some intuitive expectations. Time goes from left to right. Higher means more. Different colors mean different things. Great. So you start adding a whole bunch of metrics to your system. You instrument it like crazy, because why not? Why wouldn't you want that information? So now you have a new problem. And that new problem is, wait a minute, I have so many metrics, I don't even know which ones to look at first, right? You might have several different dimensions to look at your metrics on, and how do you look at these in such a way that you're scanning the landscape? I would say it's slightly better than logs, actually quite a bit better, but you're still watching a movie through a little keyhole. This time you have some sort of time lapse, so you can go, oh, something's going on here. So this is what we actually want. We want this picture, because all of you, within a couple hundred milliseconds, was like, oh my God, we need to go look at that guy. Something crazy is going on. She's okay. We don't need to worry about that right now. So there's not a whole lot that does this yet, but there's this really interesting project, and ironically, yes, it's also from Netflix. This is an open source project. It's called Visceral. So I want to show you this video that might give you a sense for what I mean by intuitive insight. So what you're looking at here is actually all the traffic coming into Netflix from the internet. And without any training, you probably have figured out, oh, there's fewer dots here than there are here, so there must be more traffic going here. And also without any training, you probably notice, oh, there's more red dots going on up here. Something a little fishy is going on, right? So you're using your intuitive sense. Now you're looking at it and going, oh, that's interesting. Wow, there's little dots moving over here. Maybe there's some kind of event in progress. And you can get this sort of complex picture of what's going on, but at the same time, you don't need to panic because, okay, well, the error rate here isn't incredibly high. We don't need to get all hands on deck at this point. So again, it's leveraging our low-level senses without requiring tons of cognitive effort. And so here, I'm inferring that what's happening is now the clients have failed over, right? So there's a very complex picture of what's going on with very little effort on our part to understand. So I'm just going to show you one more. This is a view of an entire one single region. It was one of those circles, and each dot is a microservice. So I don't know anything about what microservices these are, but I do know, just looking at this, wow, these dots, lines in the middle are these solid dots. These must be really important. So in terms of, oh, if I start seeing red dots over here, I better up the urgency of my, calling to the engineering team that manages the service. And I can even look at this and go, oh, well, these other teams that are, linked to it are also affected, right? Again, very little effort to get the lay of the land. So because there's not a lot in this space yet, I want to do another thought experiment with you. This is kind of just to get you thinking about how can we build intuitive insight. So what if the interactions between the components of your system sounded like cars driving down the road? So just imagine this. You're sitting on the side of the road, close your eyes, you just hear cars going by. It sounds normal. Pretty soon your attention turns toward, what are you going to have for dinner? What are you going to do over the weekend? You're not even thinking about the cars driving down the road. But then a couple hours go by, and you hear a loud crash coming from over there. So you immediately open your eyes and look over there. I'm like, oh my God. So you know exactly that when something happened, where it was coming from, and you can start to very quickly respond to that. So this is really the power of our primary senses. We're not putting a lot of cognitive effort into listening to the cars on the road. But we can immediately detect anomalies. So I'm not suggesting that, the wave of the future is that we employ humans 24/7 to listen to server traffic. On the contrary, I think this is a great job for machines. But this is kind of to get you thinking of, hey, until machines are really good at doing this, how can we better present the information about what our systems are actually doing? So just to review, we want to know at a high level, is it working? We want to scan the landscape. And I find that the tools that are most popularly used today, charts and logs, kind of inhibit us from doing that. And they really don't make use of our rich sensory signals. So we need more tools that leverage our intuition. And I think Visceral is a first of hopefully many examples of that. How am I doing on time?
15.
All right. So I want to wrap up and kind of look to the future a little bit here. So I kind of talked about a lot of challenges in software engineering, and ultimately I think these are actually very ripe for machines to assist us in doing our jobs. I think that this is going to be the first wave to get us from where we are now till some point in the future when we don't need to write code anymore, and there's machines that are either A, writing code, or B, just learning about the world and doing their job. So let's talk about a couple possible applications that I think would help us navigate this interface between infinitely precise machines and the real world with a lot of noise and uncertainty. So I think one application I'd like to see would be curiosity-driven tests. So imagine you have a test agent, if you will, and it has a set of senses and it has a set of actuators, and what it's doing is it's actuating the system under test. And really it starts out kind of randomly. It just starts, twiddling knobs and dials and just seeing what happens. It's randomly exploring your system. And then eventually, over time, it will start to build a model of what your system is and what it does. It'll form expectations about it. And so with those expectations, it can start to, map out anomalies, right? So it can go, something must have changed in the software because last week I got this thing and now I'm getting this other thing, right? The world of continuous delivery, things change so fast that it's really hard for any one person to keep up with all that. But if you had this curious agent, if you will, that was constantly poking around, it might pick up on things that, say, our limited attention spans wouldn't necessarily pick up on. And it would say, hey, engineer people, did you really mean that? Or, hey, go look over here because this doesn't look right. So I think another really interesting area for deep learning would be to basically have an agent that would help with self-healing systems. So in this case, the senses coming in are really the telemetry information about the system that's being operated, and the actions that can be performed are things like doing deployments, scaling in a more intelligent manner than, say, some CPU threshold, for example, maybe failover. And I think this is where if we can start to nail bits and pieces of this problem, this will start to bleed into more and more mainstream, maybe it's going to start doing traffic routing, right? I mean, I don't know how many times human beings have written, a router for internet traffic, but what if those algorithms were now done by these machines? So let's review. We're kind of this curious bunch of human beings that have not only to navigate the natural world and figure out this survival bubble, but we also need to navigate the working software world. And we're doing it indirectly with these generative models that today we call code. And really, what we want to do, because machines are infinitely precise, we want to get away from this model where we have this happy path notion that leads to perhaps these utterly broken states. And we want to get to a landscape that supports resilience, right? That our software system can navigate situations that we really didn't predict in the first place. And so that's the end for today, and I really want to thank you for coming, and please give me a rating.
So there's one question.
One question,
yeah.
Okay. Either I did my job really great, or I confused the heck out of you, and there's...
So is it fair? It is fair to say that logs and charts are not the answer, but visualizations instead. Do you see any limits to visualization?
So, limits to visualization. So we humans, right? We have these kind of imprecise senses, right? And we make mistakes all the time. So I would say the limitations of visualizations and animation would be kind of similar to the types of limitations that we experience in real life. Like, I've been hiking at times, and I've been looking for a rattlesnake, because where I live, there's rattlesnakes. And a lot of times I've seen a rattlesnake, and there wasn't really one. So I think, the danger of that is really just the same weaknesses that we see in the natural world, where we might see something that doesn't really exist.
And one more question. What are you working on now?
Right now, I'm actually working on trying to get agents to play video games. Actually, going back to Diogo's talk, I mean, we want to tackle some of the games that are inherently harder, that require some sense of sort of time and memory. So that's really the area that we want to tackle next.
Any other questions in the audience?
Hi. Following up on the question on the charts and logs is not good enough. It doesn't give us the whole picture, but we don't have anything else that actually does yet. So within this scenario, do you have any recommendations, something that we at least can do to leverage better the logs and the graphs and everything that we have for now?
Right. So the visceral demos that I showed you are actually available today. It is an open source project. So anybody can start to use that. I mean, it's a visualization framework, and it does operate in real time. I think what you need to do is plug in your data to it, essentially. So, I will say there is shortcomings because there's really not a lot out there yet. I'm aware that Netflix has created a team called Intuition Engineering, and so I believe that they will start to produce more and more tools in this area. I would love to just try as an experiment to see if I could get some sort of audio representation of traffic, like would we actually get it to sound like cars? So yeah, today there's actually not a whole lot. There's one project I know of, and I don't know, does anybody else know of any other amazing type projects out there? Okay.
Other questions? Okay. So let's give Julia a big applause.